Okay, so here's another example that we're going to look at here, and this is again just finding the transfer function. And in this case here, I'll make sure, of course, on an exam to specify things like this, because even though I said we're almost always going to be finding this, remember we said in the previous lesson that there are several types of transfer functions depending on what output over input you're looking for, but we are going to be looking at the output over the input here. And we're going to actually look at this problem in two different ways to do this. Now, first off, we could here, if I'm just going to put a little dot here and a dot here, I could combine these two elements in parallel and then do a voltage division. I'm not going to do that. The reason is because when I'm dealing with stuff in the S domain, I just erased a whole bunch of the circuit there. When you're doing things in the S domain, you're going to wind up with, an algebraic equation in the S domain. And once you start trying to combine things in parallel and everything, it can get a little messy. And instead, what I'm going to do is I'm just going to do a simple nodal analysis here and call this node here. Because, of course, this node would be down at ground. And then this node here would be my output voltage. And then, of course, this node right here is simply my input voltage. Now, of course, we have to do a Laplace transform of these circuit elements here. So the resistors don't change, but this 50 millihenry, and I'm going to go ahead and write it, since it's only milli, I'm going to go ahead and write this as 0.05 times S. Alright, so let's go ahead and do my nodal analysis here. So writing my node equation, I'd have V out over 200 plus V out over 0.05 S plus V out minus V in over 800 equals 0. And now we're going to, of course, multiply through by something here. Before we even multiply through here, I'm going to do well, actually, no, I'm not going to do it. I'll just say what we're going to do here. We're going to multiply through on both sides by 800s, because that's going to clear out my denominators completely. And then we'll just have to simplify some terms to get the transfer function. And we're also going to want to factor as much as possible as well. So on the left-hand side here, starting on the left here, we would have, well, 800 divided by 200 would get me 4. So I'd have 4s plus, and now let's be careful here, it's 800 divided by 0.05. So this would be 16,000, and you already probably noticed a mistake I made. 4s times V out, and then 800 divided by 0.05 would be 16,000, and then the s's would cancel, so I'd have V out, and then I have plus V out minus V in. And this is all equal to 0. So I'm going to simply just move this V in to the other side and then combine some terms here together. So what am I going to have here? Well, let's double check to make sure I'm not doing, I made a mistake and you probably already caught it. Like, something's not making sense. And the reason I'm saying something doesn't make sense is if I look at what I have right now is I have 16,000 plus 1. That doesn't really make sense. The 800s definitely cancel, but what did I forget here? There should be an s in front of these. So I'll have s times that and an s times that. That makes more sense, because now I have s V out plus 4s V out. That makes more sense. So I will still move the V in to the other side. And so I would have 5s plus 16,000 is equal to, well, let's be careful. I keep wanting to forget to write my V outs down. V out is equal to S times V in. Now, you want to make sure what you're doing is you're getting V out over V in here. So of course I'm going to divide by the V in and divide by this 5s here. So I'd get V out over V in, which is my transfer function, which is equal to S over 5s plus 16,000. Now, you'll see that a lot of times the way I like to write these transfer functions is, again, I kind of will factor this 5 out. Now, just as a side note here, first off, let me just emphasize here, this here is an acceptable answer. I mean, we want to simplify things as much as possible, but this is pretty simple. You know, this is a pretty simple thing here. There's not really much you could do as far as factoring. The one thing you want to do, though, possibly, is the idea that we really want to have a 1 in front of the s terms. And that's just because if we're doing inverse Laplace transforms. So if we were to do that, I would have that this is equal to s over, well, I'm going to factor a 5 out, and then I'd have s plus, and then you would do 16,000 divided by 5, which would be 3,200 as my transfer function. And now this is where you have to be a little bit careful with your handwriting and try and do your best job on any kind of assignments and exams or quizzes, making clearly that your 5s and your s's are distinct from each other. You can see that sometimes I get in this bad habit and my s's and 5s look a little bit about the same. So what I like to try and do is make my s's clearly smaller than my 5s. You know, and then also if I'm trying to be very careful, you know, really emphasize that it's a 5 by having that horizontal line be there. Now, this is essentially what the problem had, is what we were supposed to do. We were just supposed to do this, so we're done. But as far as, you know, something that would definitely pop up on an exam, quiz, or an assignment, there could be a part B here. You know, identify any poles and zeros. Well, we're not going to really talk too much about the poles and zeros in this course. This is, again, something that's very important when you get into controls or advanced filter design, is knowing where the poles and zeros are. In fact, in something in controls, there's something called a root locus plot, and the way you start a root locus plot is you get a transfer function, and the first thing you do is you plot all the poles and zeros. So you're going to need to know these for a controls course. So identify any poles and zeros. Well, the 0 is pretty easy. That's just s equals 0. And the poles, because once it's factored, is also easy. I mean, there's nothing to solve for these. This part literally is writing your answers down. You do it by inspection. And the poles would be s is equal to negative 3,200. Man, I just can't seem to write correctly today. Okay, so s is equal to negative 3,200. Now I'm going to do this same problem here. In fact, what I'm going to do here is do a little lasso here. So let's see here. Let's lasso this bad boy. Yes, I just called the circuit a bad boy. Okay, come on. Supposedly this was going to be faster. Does not seem like it is going faster. And now it's freezing on me. Well, what I was trying to do was copy and paste this circuit here. So I have it right back down here. And so let me just erase some of that there. So I am going to try and find the transfer function again here, but there is, and I'm going to write it off to the side here in a thing here, is that remember my transfer function is defined here in this case as V out over V in. Now this next technique for finding a transfer function is going to be very useful, and we're going to use it on the last example in the next video on finding a transfer function. If we pick a smart I'll put in quotes there, Vn or In, depending on what you're asked to find. I'll put in or In. Finding V out or I out, depending on what you're asked for again, gives us H at S. And the way to think about this for a second is to think about our Laplace transform. And we'll see what just happened there. I accidentally hit the go to sleep button on my computer here. So I don't know if the video paused recording or if it went blank, so whatever happened. But if we think about, going back to here, if we think about the fact that, okay, H at S is V out over V in, if we kind of think about what would be a nice function, we could pick anything for V in. For V in, and then find V out. Then we'd simply divide them to get H at S. But again, this is where if we think about this, looking at our Laplace table, if we use a delta function, which remember when we talked about the delta function, it was this abstract concept of a function that doesn't really exist. It's got infinite height, and the area under it is 1, and it's 0 everywhere except at 0. I mean, it's like, well, that doesn't really seem to make sense. And again, it's not so much that you want to think of it being physically making sense. It's a mathematical tool that can help us analyze problems. And this is one of the examples where it can help us analyze problems. Because remember here, if we do a Laplace transform of this, the delta function is just 1. So I'm going to write this over here. I'm going to erase this here. And I'm going to put a voltage supply here and give it a voltage of delta t. No numbers in front of the delta t or anything like that. And then we just had our discussion says that this goes to, through a Laplace transform, 1. And so H at S, as we said, is simply V out over V in. But this would just be then V out over 1, which would just simply be V out. This is also referred to as what's called the impulse response. Now there is also something called a step response as well. The step response is just having the input, as you might guess, being u at t, which is also an important topic as well, but we're going to really just focus on the impulse response. So if we do that here, the nodal equation we're going to do isn't really anything different. It's just we're going to have here V out over 200 plus V out over 0.05 S plus V out minus 1 over 800. And then I'm going to actually skip the rest of the work here, and that's equal to 0. Dot, 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 the work, we would get that h at s, well, I'll say v out at s, which is equal to h at s, and I already forgot what we got as our answer. S over 5 times s plus 3200. So now in this particular example, it doesn't make anything, I would say, faster or easier. But if you have a more complicated circuit, it can actually make things easier, because then you're not having to keep track of a V out and a V in and everything. You're just having to keep track of V out and solve for V out. So that's all you have to do then. So it makes having to keep track of things in a more complicated problem easier. All right, but we'll look at one more example here that I wouldn't call it necessarily complicated, but we'll use the impulse response to look at it.